I'd like to hand the floor over to Kurt Gagan, the Chief of the Sustainable Urban Development Section in the Environment and Development Division for UN ESCAP. Kurt?
Thank you very much, Abigail, and thank you to all for joining, and welcome to this research symposium to be held today and tomorrow. We all know that air pollution has become a common challenge across our region, and that more urgent action is needed to adopt and implement ambitious policies and effective measures to meet air quality standards. There is also, as everyone knows, a significant link between air pollution and climate change, which following the IPCC report recently remains a significant challenge, and we are not making enough progress. We're all affected by air quality, and it's encouraging to see the number of experts who are working on this issue in this region. In 2019, ESCAP member states adopted Resolution 75.4 to strengthen regional cooperation to tackle air pollution challenges in Asia and the Pacific. The resolution both recognized that more work must be done, but there is also a willingness to work together to exchange information, best practices, and facilitate mainstreaming of solutions. Now, much work has already been done to identify science-based solutions. The UNEP CCAC report, Air Pollution in Asia and the Pacific Science-Based Solutions, identified 25 clean air measures to reduce air pollution. But matching the appropriate solutions with the various causes of air pollution is essential, and those methodologies and tools to determine the causes are the focus of this symposium. At ESCAP, we are working to achieve this through a number of projects, including support to cities such as Chiang Mai and to the newly established ASEAN Resources Panel. To deliver on this, key scientific questions need to be answered. For this event, we have invited your participation because research developed by members of this group is instrumental in identifying the priority areas for action by Thailand and across the region. I would like to emphasize the importance of accurately determining the sources of air pollution so that limited resources across countries can be focused in the most effective manner. We will address in the course of this symposium a variety of methodologies to accomplish this, including machine learning and chemical analysis of PM2.5 particles. I hope that we can achieve a scientific consensus on the strengths and weaknesses of these approaches, which will enable targeted action and the adoption of the appropriate clean air solutions to reduce these emissions. Additionally, the impacts of air pollution on public health, particularly on gender-related impacts, is a major focus of our work. This area has been historically understudied, and we're pleased to see the efforts underway to fill this important gap in the knowledge base. On behalf of ESCAP, we're grateful for the work that you have all done to advance scientific understanding of these issues and look forward to the findings of this meeting and the continuation of this work moving forward together. Again, thank you all for joining, and let me turn it over to my colleague, Matthew Perkins, to continue. Matthew, over to you.
Great, thanks very much, Kurt, and thanks all for joining today. We are very much looking forward to the exchange of research and the emerging scientific consensus that we will have from these coming 2 days. We'll begin our deliberations for these sessions with the focus on the PM2.5 and polycyclic aromatic hydrocarbons. We do have a very packed agenda for sessions 1 and 2, so we would ask presenters to be sure to keep their presentations to 10 to 15 minutes. We will be pleased to circulate slides after the fact for people to make reference to, and therefore we would ask the presenters who have slides with reference materials and supporting data to transition through those slides quickly, as we will make those available for reference after the session. So with that being said, we have our first presentation today from Kun Nitipon. I'd like to now turn the time over to her to start with sharing her presentation on the influence of the zero burning policy and Ambient 2.5 patterns in northern Thailand. So Kun Nitipon, over to you, and we would ask speakers to please very briefly introduce themselves to the audience in their remarks. Thanks, and over to you.
Thank you, Matthew. Can I share my screen right now?
Sure, let me get you set up for that. Okay, great. You should be ready to go.
Okay. Do you see my presentation right now?
Yes, you're good. Please go ahead.
Okay. Good morning, everyone. My name is Natipon. I'm from the Faculty of Science, Chiang Mai University. Thank you for inviting me to today. Today, I'm going to present my paper work in the topic of influence of zero burning policy and climate phenomena on ambient PM 2.5 pattern and PAH inhalation cancer risk during direct episode of smoke haze in northern Thailand. So actually you can see the more detail in this paper, which published in the Atmospheric Environment Journal in 2020. Okay. And before I start with the air pollution in Thailand, so this is show you the PM 2.5 concentrations all over the world, and the color shade here, and the green one is mean they're higher than the standard, WHO standard. And today we focus in Thailand. How about in Thailand? So in Thailand, annual PM 2.5 concentration is around 25 to 35 microgram per cubic meter, which is higher than the standard of Thailand. And of course, it's higher than the WHO standard for 2 to 3 times. And this is the situations of PM 2.5 concentration in Chiang Mai City. So this data obtained from the Pollution Control Department, or PCD, at Chiang Mai Station. So they were plotted since 2011 until this year, and this is the highest concentrations was found in 2015 and 2019, 2016, and this year in the yellow line here. And you're going to see that this is the pattern of PM 2.5 in northern Thailand. So you can see that they reached the peak in this period, which is the dry season in this area, February, March, April, in here. And after that, the concentration is acceptable for the Thai standard at 50 microgram per cubic meter, right? And here, this is the annual average that just separate into graph. So the black one is represented the average PM 2.5 during 3 months, February to April. And the blue one represents another 9 months, which is a non-smoke haze season here. And after we average for the annual for 1 year in the gray background here, that makes the annual average PM 2.5 is lower than the standard in this line here. You can, from this graph, you can see that the only 3 months of this smoke haze can make the annual PM 2.5 over the standard here. This is our problem for this area. And PM2.5, or the particulate matter that we know, this is the definitions of the particulate matters. In the past, we focused on PM10, and right now we focus on PM2.5. And this one shows the particle that observed under the SEM. So this is from ambient air in Chiang Mai. So you can see that this is the particle, just only 1 micron, which is smaller than 2.5. And in terms of the health effect, you can see here, if you focus on PM10, it can affect upper respiratory tract. And PM2.5, it can reach lower in the lower respiratory tract. And if it's PM1 like this, it can be reached alveoli, like a sac that exchange the gas in our lung here. And if smaller than 0.1 here, is just the smallest one here, it can be reached in the whole body, so they can go to bloodstream. So this is the risk of the PM based on their sites. And here, for Thai government, they try to solve this problem. So you can see here, this is the cycle of the air pollution that I try to explain here. So the air pollutions occur from the source here, the source. So actually, nowadays, sources come from humans. We make a source of air pollution and release into the atmosphere. They have the reactions or just directly the source occur the air pollution in this area. And after that, we note the problem because they have the effects on us, especially on humans, like health. And the government tried to reduce the source here. So that's why they implement the zero burning policy. So the aim of the zero burning policy just to control the air pollution problem by reducing open burning. And the target of this policy just only 9 affected provinces in the northern Thailand here that I highlight here. And the implementation year since 2016 to present. So this policy did not implement in the whole year, just only for some period, around February to April, which depend on each provinces actually. And this is the result from our study. We try to compare between PM2.5 concentrations, this kind of daily PM2.5 concentrations here. Actually, this is what get from the Chiang Mai PCD at Chiang Mai here since 2012 to 2019. We can separate in the two period here, before policy implementation and the years of policy implementation here. You can see that we're going to start with 2012 to 2015, which didn't have any policy. And you can see that the peak of PM2.5 concentrations is occur around middle of March and April here. They start around the beginning of the March and reach a peak, and after that they reduce here like this. So this is the same pattern of this year. And after policy implemented here, and you're gonna see the peak was changed. The pattern of PM2.5 was changed. It's like a no peak here, no peak in 2000. No peak in 2016 to 2018. It's kind of like a flat curve here. And moreover, you look at the 2019. You can see that the peak here again, which is this pattern is like the years before zero burning policy, right? So, and after that, we try to compare with the fire hotspot count, which is to detect the open burning, because we see we know open burning is the major source of the air pollution in this area. So we can see that there are the relationship between the patterns of PM2.5 and the pattern of fire hotspot. You will see that this year, the pattern of hotspot is reached a peak in the March as well. And in this year of the policy, the pattern of hotspot didn't have any peak like the years before that. So the one more thing that we can observe from this result, after we implement the policy, you will see that the patterns of PM2.5 as well as the fire hotspot count was prolonged more than 1 month from the previous year. Yeah, it's quite long, but it's lower concentrations. So moreover, we just observe about the global climate that might be effect on the PM pattern here. And you see, for example, I'm gonna give you an example here. This year, 2016 and 2017, 2018, which is the La Nina years here. So same as the 2012 here. So this year we have the policy, zero burning policy that control the open burning. You're gonna see that the fire hotspot was reduced compared to 2012. So it can be said that the policy effective in this year. But in 2019 also used the policy as well, and compare with 2015, which is the same climate, right? El Nino, which is the same climate. But the policy didn't effective in these years, because you see from the number of hotspots is higher than, a little bit higher than 2015, which is not implementations of the policy yet. Here, okay, and here gonna show you the land use and the open burning from each year. So like for example here, 2015 and 2019, which is the same climate, is El Niños. So that's too much higher in the number of hotspots in Thailand and our neighbor country here. Right. So for in Thailand, most of them are the forest area in the northern part here. And this one is 2017 and 2018. You can see that the climate and the policy was different from this year. You can see the fire hotspot was reduced in these 2 years. Okay. So from this observe, we just got the result, like the implementations of the zero burning policy has an impact on the patterns and evidence of the open burning, and the policy result on PM2.5. Okay. The policy result on PM2.5 level reduced, but a prolonged smoke is darling for 2 months, and the climate condition include ensocycles and relevant meteorological conditions were the main factors affect on PM2.5, and this is the part of the PM2.5, and then this is our study, and in the same study, actually we have the air pollution as we have the air quality stations for 2 stations in northern parts of Thailand. Here it is in Chiang Mai, suburban area at Chiang Mai, which is represent the area that near burning source, And another area is a rural area, which in the Nan, which is represent the near agricultural residues burning source. And here, this is our station at Chiang Mai and Nan. And this is the sample that we collect. This is the PM2.5 sampled on the filter for 24 hours. So we can get the PM2.5 concentrations by gravimetric method. And then this sample will go to chemical analysis. In my case, it's like of the pH analysis. So, and here, this is the pH that I mentioned. So actually, they can classify as the carcinogenic compound. That's why I'm interested in this compound. And you're gonna see here, this is the PM2.5, and the bar graph is the pH. You can see the correlate with the compound, the chemical compound on PM2.5 in both sides here. And this pie chart represents the carcinogenic and non-carcinogenic pH. The carcinogenic pH represent in the hot color, like a red one. So you can see the high ratios of carcinogenic pH per sulfur. Right? And after that, we try to assess the health risk based on pH concentrations. You will see that PM2.5 from both sides were not significant difference, but the pH was really significant difference, especially in non-stations that were 2 times higher than Chiang Mai. So after we calculate the inhalation cancer risk assessment, we're gonna got this value. So that means at Nan is high risk based on pH concentration, and Chiang Mai is medium risk. Okay, and from this result we can say that it's not only particles, but we have to concern about the chemical compounds on the PM2.5 as well. And finally, pH can also identify the possible sorts. So in this case, I used some isomer of pH. So the results show you that the diagnostic ratios of some pH reveal biomass burning as the major source like this. Okay. So this is all of my presentation. Thank you.
Great. Thanks, Nitipan, for that very useful summary of the research in this paper. We'll have a couple of points briefly from the Secretariat on your findings, and then open the floor if anyone would like to pose a question at this stage. So some of the points that we see from the research here is that the meteorological effects have a significant impact on the observed patterns of PM2.5 concentrations, and that these remain an important area to include in analytical work moving forward. Also noting the identification of biomass and coal as the principal sources of the PAHs in the scope of this study. With regard to the impact of the burning policy of Thailand, one thing I would like to ask for your views on is the need to include long-range chemical transportation and transboundary biomass burning data in the overall analysis to correctly understand if, for example, fires in Thailand are reduced, but fires in neighboring countries are increased. How will this affect the ultimate levels is the first question. And then the second point, which I would like you to speak to, although perhaps the next speaker will also address the issue, is that in the chemical analysis of the PM2.5 particles, I'd like to get your views on the use of potassium ions as a marker for biomass burning, particularly on levoglucosan ratios, in order to correctly understand the proportion of open burning contribution to the PM 2.5 levels. So if you could correct any of the summary points I have given, please do, if I got anything incorrect, and speak to the point of the transboundary analysis and the use of potassium ions to identify sourcing. Please, over to you.
Okay, okay, thank you. For the long-range transport, like a transboundary here, do you see in this picture? Actually, in this project, I also address this point actually, but this is just from the wind directions over there here. So if in this area have the burning, and of course it can affect the whole area. So that's mean the long range transport and also affect the air pollution quality in northern Thailand as well. And for the potassium marker, actually we can kind of use this chemical we can use this chemical to like identify the source. So in case of the pH, it's just the possible source, but for the potassium, I think it's more correctly than using the pH. Yes.
Okay, great. Thanks very much for that. And I believe we will also be hearing more on this throughout the session, particularly from Khun Somporn as well. Therefore, as I open the floor to anyone who would like to pose any questions on your paper, I would ask just very briefly, Khun Nittapon, if you could identify one key area for next steps in the research that you would like to recommend to our consideration. Thanks.
The key areas, right? So what the means of
for the next steps to extend your research work, what should be done next?
Okay. I think in the northern, it's we just research in the northern here, especially in Chiang Mai. And right now we try to expand the areas, the study area to cover the northern part. So the one parts that actually have more effect in the central parts. So because in the later 2 to 3 years, air pollution is quite severe in the northern parts, in the central parts as well. Yeah.
Great, thank you so much for that. We really appreciate your inputs on this point. I think in the interest of time, and as I don't see any hands raised at this stage, let's go ahead and thank you very much for this very informative presentation. We'll now recognize Khun Somporn as the next speaker. Somporn, if you could please share your screen, give a brief introduction, and begin with your 15 minutes. Thank you so much.
Okay, thank you, Matthew, for your kind introduction. I may share my slide. Ms. Nittapon, could you please stop your sharing? Did you now see my slide?
Yep, looks great. You're good to go. Thank you.
Still see as the full screen, right? Okay. Good morning, everyone. My name is Somporn Chantara from the Environmental Science Research Center, Faculty of Science, Chiang Mai University. It's my pleasure today to give a presentation on the newest paper of our research lab. So the paper entitled Fresh and Aged PM 2.5 and their ion composition in rural and urban of northern Thailand in relation to source identification. This work is a part of the big project so-called the monitoring of air quality and smoke haze situation in Upper Northern Thailand for assessment of health and environmental impacts. This project was funded by TSRI or TRF. This is the first page of our paper published in Chemosphere. And I'm going to go to the detail of that. First of all, I would like to talk about the objectives of the project. The first one is to monitor ambient PM2.5 from traffic and biomass burning source. The second one is to analyze water-soluble ions of PM2.5 in relation to their emission source. And these are our sampling sites. So we select 2 areas, 2 representative, the urban sites, and 2 rural sites in Chiang Dao and Mae Sariang. So we have 3 provinces. The first one is Chiang Mai Province, and we have 2 areas, Chiang Mai City and Chiang Dao District, and 2 rural sites. In Chiang Mai, we select Chiang Mai City and Chiang Dao District, and for rural site, we select Mae Sariang to compare with Chiang Dao, and for urban site, we select Lampang to compare with Chiang Mai. And this is the detail of each sampling site. For the first one, Chiang Mai City, so we select the Northern Meteorological Center to be our sampling site. It's located near the Chiang Mai International Airport and can represent the traffic emission. The second site is in Lampang Province. We put our samplers in front of the Bunyawat Vidyalai School. This is a big school of Lampang Province, and this site is close to the road. And for the rural site at Chiang Dao District, we set up our station in the middle of the agricultural farming activities to represent the open burning. For Mae Sariang in Mae Hong Son, we put our sampler at the meteorological station of Mae Sariang, and also it's located at the open field. For the sampling, we do the 24-hour PM2.5 samples every day in the haze season, and also some days in the wet season and the cool, dry season to represent the whole year. And we use 2 equipment. The first one is the low volume air sampler with the flow rate of 16.7 liters per minute. And the second one is the mini volume air sampler with a flow rate of 5 liters per minute. And here are our PM2.5 samples. After that, we analyze by extract the filter papers and using the ultrasonication and analyze by ion chromatograph. And then we obtain the cations and anions in these chromatograms. And here is our result. The graph showing the trend of PM2.5 in each sampling site. So the line graph you see here is the PM2.5 concentrations, and the red bar graph represent the 5 hotspot counts in northern Thailand in daily basis. And if we compare the average concentrations of PM2.5 in each sampling site, we found the highest concentration at Chiang Dao Station, followed by Lampang, Mae Sariang, and Chiang Mai at the end. We found a good correlation between PM2.5 concentration and the 5 hotspot counts in overall. And if we take a look at the 5 counts again by province in northern Thailand, we will see the very familiar patterns. Most of the open burning occur in the dry season, particularly starting in February, highest in March, and again in April. And at the end of the year, we will see some open burning occur already. In 2019, we found more open burning in Lampang and Tak province, for example. And these graphs show the correlation between PM2.5 and their ion composition at each sampling site. The line graphs here is the PM2.5 concentration, and the bar graphs are their ion composition. So we see very similar patterns and see high correlation between PM2.5 and their ion content in all the sampling sites. And if we transfer the concentration of ion concentrations into the percentage ratio and divided them into season, starting from hot dry season, wet season, and cool dry season, we see the changing of the portion of the ion content, and noticeability, we will find very high portion of secondary inorganic aerosols in this slide. For example, we find nitrate, sulfate, and ammonium, which is secondary inorganic aerosols. For potassium ion that Matthew has mentioned in the last presentation, we also find it here in the blue column here. And of course, we always use it as the biomass burning tracer. When we compare the results of this study with our previous work, at that time we performed the open burning simulation using the constructed open system combustion chamber like this one. And we calculate emission factors of PM2.5 and also the chemical component from the open burning by using different types of biomass. And we found the potassium and chloride very high, particularly from the agricultural residues burning. In this study, in relation to the previous one, we make a conclusion that the potassium chloride can be represent the young and fresh aerosols, or it can be called as primary pollutant, while the potassium nitrate and potassium sulfate can be represent the aged aerosols or secondary pollutants. This is similar to the result from Lee in 2003. So as I already mentioned, potassium chloride will be used for a tracer for fresh aerosols from biomass burning, and potassium nitrate, in our case, is a tracer for aged aerosol from biomass burning. And this graph shows the correlation between potassium and nitrate with PM2.5 concentration. And we found a positive correlation between the potassium and nitrate with PM2.5. So we can conclude that potassium nitrate contributes more with the increasing of PM2.5. On the other hand, we also plot the correlation between ammonium and sulfate with PM2.5, and we found negative correlation. In this case, ammonium sulfate contributes less with the increasing of PM2.5. And from this data, we can say that contribution of biomass related sulfate to ambient PM2.5 in northern Thailand were relatively less comparing with the potassium and nitrate. And during the smoke haze season, the increasing of PM2.5 was mainly contributed from open burning or potassium nitrate rather than from traffic emission. And when we take a look at the source identification based on the principal component analysis or PCA, the first component we found secondary inorganic aerosol mixed source by judge them from the components that we found. So we found both SIA and biomass burning in the urban area of Chiang Mai and the Mesariang rural area. Then for the Chiang Dao, this is very special. At Chiang Dao, we found both primary and secondary biomass burning because we found potassium chloride and potassium nitrate. And this study, our study, is well agree with the study from Gale in the 2016. At that time, they conducted a study at Doi Ang Khang in Phang district in Chiang Mai Province. And we can say that in the urban area, with or without biomass burning influence, we still can find secondary inorganic aerosol, both like ammonium and sulfate. And in some study, they also find nitrate as the tracer. So urban area also, both in hot dry season and in other seasons, we found the same results. And I come to the last page, to the conclusions. So we can say that there are no differences in ion composition of ambient PM2.5 during the heat season in northern Thailand, except where the open burning is most intense. In this case, Chiang Dao rural area is the example. Area with very high open burning had prominent primary pollutants with potassium chloride as a main tracer or fresh aerosols emitted from open burning. And the secondary PM2.5 is dominated during the haze episode due to prolonged accumulation. Potassium nitrate is a tracer for aged aerosols from biomass burning, as potassium chloride eventually turned to potassium nitrate as well during the aging process. Ammonium sulfate and potassium nitrate are main compounds in ambient PM2.5. And the sources of PM2.5 during non-smoke haze season depend very much on local activities. The secondary ions, for example, ammonium sulfate, was found in urban area. And the biomass burning tracer, for example, potassium chloride and potassium nitrate, are found in rural area. So thank you for your kind attention. I hope I keep the time. Thank you.
Thank you, Khun Somporn. Really an excellent presentation. And I must say it was a struggle for us as the Secretariat to determine which one of the papers from your group to invite for this conference. And we're very pleased that you have made such an effort to draw from all of them in your presentation, which is very helpful. In the notes for our review, I'd like to confirm one of the key findings that really stood out to us from your work was the importance to properly segment by season the dimensional analysis. I think the distinctions that you identified between the hot, dry, hot, wet, cool, dry, and cool, wet seasons were very insightful. It therefore appears that an emergent finding from this is that the use of annual or semi-annual averages only can conceal important insight that could otherwise be determined by examining the seasonality as was done in this paper. Likewise, we take note of the importance of considering the potassium ion emissions and the metabolites in order to identify short-range biomass and long-range biomass contributions to PM2.5. Please confirm if this summary is correct. I'd also like to ask, based on the totality of the work you've presented, could you please give your views on whether it is achievable to identify which particular crops are identified in the chemical analysis of the PM2.5 particles, with particular interest, of course, to the PAHs released in those combustions, as we understand from your work that some crops emit far more PAHs when combusted than others, along with factors such as fertilizer use. Over to you.
Okay. Actually, your question is not related well with this paper, but we have another paper that I sent to you. At that time, we performed the open burning simulation in the combustion chamber. And at that time, we collect different types of biomass from the field. For example, we collect the rice, straw, maize residues. We collect the leaf litters from different kind of forests. And then we perform the open burning, and we collect the PM2.5 samples that emitted from the open burning. Then we analyze them. We analyze ion compositions and also PAH composition. And we found different types of emission. For example, in case of ions, we found high potassium and chloride ion from agricultural residues, both from rice straw and maize residues. But for PAH, I did not bring the data today, but as I remember, we also found high concentration of PAH in all types of biomass burning. In terms of identify between the types of biomass using the tracers we found, we also presented our finding in the papers that we can use potassium and chloride and sulfate, for example, to identify between agricultural residues burning and forest leaf litter burning, but not the pH. So I hope I answer your question.
Great, yes, thank you very much. That is very helpful, and I think this will be a fruitful area for further research and examination. I think having the test bed chemical profiles is a really valuable reference for further understanding and study of this issue. So thank you very much for this rich and helpful presentation, and we look forward to receive your thoughts on the other presentations in the session. We're running about 10 minutes behind, and I don't want to steal too much time from Kun Siwat, who is our next speaker. So please, Kun Siwat, over to you for your presentation and a brief introduction. Thank you.
All right. Thank you, Matthew. So I'm going to share my presentation. Okay, I'm not quite sure whether you can see my PowerPoint presentation or not.
We do have it, but it looks like it is not in presentation mode at this stage. I think you're sharing your desktop as a whole.
All right. Windows. So now, can you see my presentation or not? No, not really.
It's still coming through as a desktop share. I think we could have Abigail share the slides if there are any technical matters on this.
Yeah. Entire screen. Okay. And all right. Now I hope you can see my presentation. It's an entire screen. Still. Oh.
No problem. Let me see if I can help you on that.
No file builders. No, don't know why.
Okay, I believe we would now be having the first slide of your presentation on the screen. Abigail, can you confirm that?
Yes.
Yes.
Okay, great. Let's go ahead.
All right. Okay. So I apologize for some technical problems. So today I would like to present my papers published in APR, and the title is Effect of Agricultural Waste Burning Season on PM2.5 Bound PAH Levels in Northern Thailand. And this research collaborate with IEECAS in Xi'an, China. So yeah, I'll start with this question: why should we care about PM2.5? And I think everyone in this panel know it. But it's not only focused on the lung cancer, or they also have many diseases related to the impact of PM2.5, such as stroke, lower respiratory infections, diabetes, liver disease, and chronic kidney disease, and also Alzheimer's disease. And as you may know, the PAH is one of the carcinogenic substances, and they have many contributors. And so the question is, what are the main contributors of air pollutants in northern Thailand? Yes, agricultural waste burning and forest fires are one of the main contributors, but they also have other sources, such as local traffic emissions, and also maybe industrial emissions in some part of the provinces in northern Thailand. And you already mentioned about the long-range atmospheric transportation from the neighboring countries. But the question is about, we are looking for a short-term or a long-term monitoring. So the certain period of time, like if you are looking for a specific time, like in haze period, of course, biomass burning will be one of the main contributors. But if you are looking for the long-term monitoring, maybe we will see some sources like traffic emissions, or maybe the trans-boundary could be one of the another major contributors. And if you're looking closely for the intensive sampling campaigns to see the differences between day and night, like diurnal variations, that could be another point. So in this study, we're looking for 9 administrative provinces by using the air sampler, the low air samplers, and we are using the PCD air quality observatory sites for monitoring. And this is the steps that we use for the substrate extractions, and we also use the internal standard to quantify, and finally use the GCMS QP 2010 with the SSP system of Shimatsu. And of course, for the QA/QC, we use the NIST National Institute of Standards and Technology SRM 1941B for quality control and quality assurance. And also, I would like to explain about the toxic equivalency factors, or TEF. And this is, there also have many formulas that we can use to quantify and to normalize all different PAH containers to benzoapyrene. So we are normalized to benzoapyrene. As you may know, that benzoapyrene is one of the most toxic PAH, and we use the value of 1. And therefore, all the pH containers will be calculated in relative to the toxicity of benzoapyrene, which is 1. So we have 3 different formulas that use, but in this study we use the Nisbet and Laboid formulas to normalize all the pH containers to benzoapyrene. And this is the result that we had done in northern part of Thailand. So this is the average of 9 administrative provinces in northern part of Thailand, and we separate the sampling periods into 4 categories. So the first one in 2012 during the non-haze seasons, and the phase 2 in 2013, phase 3 in 2014, and phase 4 in 2015. As you can see, that there are some significant differences of benzo B and K fluorantine. And if you look at the sum of the 5 to 6 ring PAH, they also have some significant increases in 2014 and 2015. So the phase 1 and phase 3 was monitored during the non-haze period. So the phase 1 is from 7 to 22 December 2012, and the phase 3 is from 16 December to 2014 to 10 January 2015. And this is the phase 3 and phase 4. And as you can see that they have some increase of the benzo B and K fluorantine from 2014 and 2015. And when we normalized all the pH containers to benzo A pyrene, and we again calculate the percentage contributions of each pH containers, we will see the results as displayed in this graph. So again, the impact of benzo B to K fluorantine is also significant during the year of 2014 and 2015. When we apply the diagnostic binary ratios of PAH by using the ratios of fluorantine and pyrene and anthracene and phenanthrenes, and to see how it related to other samples collected in other continents, like in European countries, in North America, in South America, Australia, and Africa. So as you can see that this is the northern part in N1 is during the haze episode and non-haze episodes. And you can see it's still fall down in the categories of petroleum combustions. When we apply other type of
it's 10 o'clock,
like indinol and benzo GHI-pyrrolene and benzo A anthracene and crisanes, still we can see that there are some effects from petroleum combustions to during the both episodes. And when we apply the 3D plots of principal component analysis, we can see that the results that we obtained from this study in northern part of Thailand are quite prominent. That we have a different profiles comparing to other parts of the world. Now we compare our results with the sample experiment results from other studies. As you can see, when we apply the anthracene and phenanthrenes and fluorantine and pyrene, and this is the sugarcane burning for in this area. We also have the result from plastic garbage burning, and also the diesel emissions, and the rice straw burning, and the agricultural waste biomass burning groups. Now, if I look very closely to our results determined from phase 1, 2, 3, we can see that they are quite pretty close to the groups of the diesel emissions and also the motorcycle exhaust and the mixture between the paddy fuel burning and biofuel emissions. Now we changed the containers to benzo A anthracene and crisanes, and benzo A pyrene to benzo A pyrene. And again, if you look pretty closely, the results detected from phase 1, 2, 3, and 4 are pretty close to the tunnel experiment, which means it's come from traffic emissions and also the motorcycle exhaust. And again, now we changed to benzo BK fluorantine and indinol, and also the benzo GHI-pyrrolene. And we can see that the phase 1 and phase 2 are again pretty close to the mixture of motorcycle exhaust and the heavy duty and light duty vehicle emissions. Now, we are trying to plot individual pH container to the total pH and see how the slope and the intercepts and also the R-square values change. As you can see, if we plot against the data that we collect from all the urban atmosphere, we see the relatively high R-square obtained from the anthracene, benzoyl-anthracene, cresene, benzoyl-E-pyrene, benzoyl-A-pyrene, indeno, and benzo-GHI-prilene. Why we are on the contrary, why we plot all the individual pH container against the total pH and using the value from biomass burning experiments from other studies, we see some high correlation coefficients of R-square only for phenanthrene and benzoyl-A-pyrene. Now we move to the principal components, and we use the Varimax rotated components applied to PM2.5 bound pH from the 9 administrative northern provinces during the HAZE period, which means the phase 2 and phase 4, and the non-HAZE period, which means the phase 1 and phase 3 periods. So now we can see at the principal component 1, we see a relatively high eigenvalues, the variance of 53% and and 55%. And most of them show a relatively high correlation coefficients of phenanthrene, fluorantine, pyrene, benzoyl-anthracene, and cresene. I mean, both of the seasons, which mean the non-HAZE period and HAZE periods. And phenanthrene is pretty well known as the proxy of the diesel emissions. Together with the other fluorantine and pyrene is also PAH containers, which is the proxy of the traffic emissions. So now if you look for the second component, the principal component 2, we see the relatively high correlation coefficients of benzoyl BK fluorantines and benzoyl A-pyrene in the second component. Now the conclusions. In conclusion, all data analysis, which means we use the diagnostic binary ratios, the linear regression analysis, and the PCA principal component analysis. So it's highlighted the importance of traffic emissions as one of the major contributors of PAH containers in northern Thailand, irrespective of HAZE periods. But you have to bear in mind that the monitoring stations of PCD is relatively located close to the traffic roads. So that which means it might be affected by the traffic emissions all the time, even in the middle of the HAZE episodes. And the number of vehicles has increased considerably, not only in the city, but also in the rural area in the past 5 years, as a consequence of the so-called the first car buyer scheme in Thailand. And it is worth mentioning that the source apportionment results of this study is limited to only PM2.5, which means the field works should be focused on all the particle sizes, such as nanoparticles. And we also have some recent publications related with PM2.5 and PM10. And as previously mentioned about the application of potassium as a proxy of biomass burning, we already published these data in these 3 papers in APR and also in aerosol and air quality research and polycyclic aromatic compounds. And the recent study, I used the synchrotron light research to characterize the impacts of shipping emissions on the variations of PM10 bound elemental species, and also looking for the relationship between COVID-19 infected numbers and PM2.5 level in Ambient and Bangkok. So thank you for your attention.
Thanks very much for this, Quincy Watt. There's obviously a wealth of information here and a very robust analysis. I'd like to summarize a few points and then open for questions on your presentation and anything in session one. We were very struck in looking at the analysis that you'd undertaken on the toxic equivalency of the significant differences among and between the regional analyses. Therefore, it appears to support the conclusion that it is quite important to take a locally calibrated perspective to the understanding of the toxicity of the PM2.5 particles in particular cities, countries, and subregions. So please confirm if we have summarized this finding correctly. As well, I would like to confirm from the total context of the research that you've done and indicated in your presentation that there is a consensus point that the use of potassium and potassium metabolites is a key indicator of the prevalence of biomass as a contributor in parallel to the toxic equivalency work which you undertook. So just that summary and question from our side, and then we'll open the floor in general. Thank you.
Thank you. Thank you for your comments. Well, actually, there are some few points that I would like to remark. First, the paper you select for me to present today is already published. The data used in 2015, which means it's 6 years ago. And therefore, the analytical results, I mean, the analysis of the contributors would be different from what Ajahn Sumpon and the other professors presented today. So that's one point I would like to highlight. And however, my recent publications, Dr. Xu Shui, she's one of my students. We are looking for the effects, the impacts of agricultural waste burning on PM2.5 bound PAH, and we use the WSIS or water-soluble ionic species together with the organic carbon species and PAH to see to conduct the source apportionment, and we still again see a significant contributions of traffic emissions throughout a year, because this is the 1 year monitoring, and we conduct this study at Doi Internon with the facility of NARIT, National Astronomical Research Institute of Thailand. And the other studies conducted in Bangkok and in Phuket are pretty similar, that throughout a year, traffic emissions is still the main contributors of PM2.5. That's what we found in this study. And the second contributors are biomass burning. So and for the local studies to evaluate the impact of the toxicity of PAH, I think this is one of the future works that we, our group, are quite interested in. Thank you.
Okay, great. Thanks very much for that. And we certainly look forward to seeing the updated work in this very key area, particularly as we continue to develop the research that we will review in the next session on air pollution and public health. It certainly seems likely that the toxic equivalency must be clearly understood in order to accurately map the burden of disease resulting from those particles. Therefore, can I confirm that it's your recommendation to the Secretariat that the future work in this area should focus on correctly understanding the comparative impact of the toxic compounds in the PM2.5 exposure in Thailand?
Yes, I confirm that.
Wonderful. Thank you so much for this submission. We're very grateful for you sharing your research with us here today, and look forward to carrying it further. I believe also as well in the coming session that Dr. Kim's presentation, I believe, will also examine some of these questions more specifically from the Bangkok perspective. So at this stage, we're a little bit off time. We're thankful for everyone bearing with the meeting. We have recorded the recommendations and emergent consensus from session 1, which we will now conclude. So unless there are any further comments, please feel free to indicate by raising your hand. We'll now transition over to session 2. So Abigail, back to you. Thank you very much, and over from my side.
Apologies and hello everybody. For session number 2 today, our moderator will be from the Stockholm Environment Institute, Ms. J, who is on with us now. We'll have 4 different presentations. Again, we would like to ask the presenters to keep their time slots as tight as possible to allow time for questions and answers. Also to our guests, reminder that you can put questions in the chat or raise your hand at any point in time. And I would like to hand the floor over to Ms. J. Nakom now to tell us a little bit more about session 2 and begin with our presenters. Jay.
Thank you. Thanks, Abigail, for the introduction. And hello, everyone. Welcome to session 2, which is application of data science and machine learning to air pollution impact. This session intends to provide information on the identification of methodologies to obtain and analyze data to determine the key drivers of air pollution in specific urban contexts. This will include remote sensing, ground-based measurements, and impacts on public health. So in the interest of time, I would like to hand over to our first speaker, Khun Pham Thao. I'm sorry if I've said it wrong, but over to you.
I believe that Khun Pham may be having some connectivity difficulties this morning. Therefore, may I suggest that we could proceed directly to presentation number 2 from Khun Kim, please.
Thank you. So, Thao, you're not around? Okay. So, if you agree, I will go ahead with my presentation. Right. Let me share my screen. Where can I share the screen?
Kim, if you go up to the right-hand side of your screen by where it says leave, there's a rectangular box with an arrow in it. Great.
Good, good. Now, I'll share my PowerPoint. Okay. Is it on now?
It is on, but
Yes.
if you could go to presenter mode.
Okay.
Perfect, thank you.
Okay. Let's see. You see it, right? Okay, let me talk about the integrated assessment of PM2.5 pollution and health impact in Bangkok. So my name is Kim Wang, so you call me Kim or Kim Wang is fine. And I have on the contributor for my project teams. So Today I will talk about the monitoring and source apportionment for PM2.5 in Bangkok from our AAT JICA project. We talk about emission inventory for BMR and WAP CAMEX simulation and benchmap CE for health effects due to PM2.5. So the situation of PM2.5 in Thailand, you already know one of the situation. The level is quite high in many places, and Bangkok and vicinity is here, the level in different years. In January 2019, the haze episode persistent in Bangkok caused a lot of public concern and attention from the authority, from public. And you can see the levels up and down during a week. January 2019, and this is 24-hour PM2.5, which is far above the peak is far above 50 microgram per cubic meter, which is the Thailand standard. And of course, all of that above WHO guideline of 25 microgram per cubic meters. And when you look at the causes, we normally look at emission. So we have intensive emission from open burning, from industry. This is for illustration only, right? From traffic, from cooking in the street. And of course, the meteorological impact is very important. So stagnant air causes a lot of build-up of high pollution. And then you can see here the picture of people in Bangkok that time wearing masks, not because of COVID, but because of PM2.5. And the level, actually, if you look at air quality index, is unhealthy in many locations in Thailand, in Bangkok. So talking about PM2.5, first we need to highlight a complexity of the problem. So here we have particles that we find a mixture in ambient air. It comes from primary source. It means directly emitted from the source that our colleagues in the first section already mentioned. We talk about ECOC, C-zone. We talk about road dust, fly ash, etc. That is primary particle. But a huge amount of particles in the air form from secondary. It called secondary pollutant. It means form from chemical reaction in the atmosphere. And then you can talk about ammonium nitrate, ammonium sulfate, potassium sulfate, and nitrate that talk, Achan Sampon talk about that right now. And very complex photochemistry with involving organic say matter that also form particles. So the particle affecting health, a smaller particle can go deep in our lungs and affecting our health. With nanoparticle can get actually into the blood-brain. And it caused PM2.5 globally caused more than 4.2 million deaths in ambient PM. And majority of the deaths, nearly 60%, is occur in East and Southeast Asia. And in 2019, so the new research from Health Environmental Institute published that the deaths due to PM2.5, ambient PM2.5, 4.14 million, but for household PM2.5, 2.31 million. So making it more than 6 million of deaths due to PM2.5. So our AAT JICA project, it named it a study of urban pollution. So that is the name of the project. And what we plan to do in this project, actually we focus more on monitoring activity. So we did monitoring for at 2 sites. And then we have one is in AAT, representing suburban area, and one is in PCD station, representing urban environment. So we use filter packs. This is integrated weekly sample. It means every week we change the filters. It means every week one sample. The filter pack is used in net, and then it has it can collect PM cost fraction, PM2.5, and can collect gases. So these own gases are analyzed mainly for acid deposition too, but we focus here and more presentation on PM2.5. So this is monitoring activity. We collected sample at 2 sites for 2 years, and we analyze for level, composition of PM, and use it for receptor modeling and find contributing source. So this is for policy recommendation. We also use emission inventory. This is not really a part of the project, but this is study from AIT. So we have emission inventory for VMR for 2016. And then we prepare that emission inventory and run the WAP GAMEX, is the dispersion model, and find spatial distribution of PM2.5 and VMR. And we use the benchmap CE, the US EPA model, to quantify the health burden. So for policy recommendation, you can see both source apportionment, also can go to policy recommendation of key source. So emission inventory also give you key source, but it's local. And WAP, GAMEX, and health effect also can go to policy recommendation. So the monitoring results show this is the PM2.5 mass. So this is our site, AIT, the red color, and the PCD is the blue color here. And then this is the data from other stations done by Pollution Control Department. So you can see that, okay, the level actually quite repeating, especially late in the year. This part actually the pollution PCD data has some problem, but later on they are monitoring also very smoothly, and then we can find that we can see the high level during the dry season, like winter and summer of the local summer and winter time, and low level during the rainy season. And the level of obtained by our sampling methods, it's also quite consistent with the level by PCD reference monitor. So for PM composition, we analyze for elemental carbon, organic carbons, iron, water soluble ions, inorganic, and element, 20 elements. And this to show you the ECOC. The EC actually gets a very much of attention because of it is defined as short-lived climate pollutants. And we find it very high, especially in AAT. So in dry season, we can find it at 4.7 microgram per cubic meters of the EC. And OC could get to 7. And in wet season, the level is lower. And this is in PCD, in dry season and in wet season. So EC and OC seem to be huge components in the PM2.5. So for receptor models, so we actually run the CMB and PMF, but this is result of CMB. The PMF results are being finalized right now. And this is showing the sources. Okay, so PCD in the wet season, the mass is around 15 microgram per cubic meter, and 18 wet season, the mass is quite similar too. So the key source in the wet season, you can see also biomass burning, you have traffic, and we have the inorganic, secondary inorganic air zone. And this is mainly ammonium nitrate and ammonium sulfate. So similarly in AAT, we also found very similar picture of the composition, contributing source factor. In the dry season, the mass getting much higher, okay? And especially in AAT, we find a huge amount of the biomass burning. So this 41%. And this is mainly burning season of rice straw around AAT. And one of the key things here is that we always thought that AAT would be cleaner than city center, but in fact it's not. So AAT is almost the same level. So we published this paper already. So Narita et al. So for the emission when we find the contribution from source in the domain, it means in the BMR, in Bangkok and surrounding provinces. So this is result for 2016, and we'll find this is the total annual emission from BMR. And PM2.5 is 42 gigagram. It means 1,000 tons per year, right? And primary organic carbon and black carbon, it means element carbon here. And we also have other pollutants. So this is to show the share of different sources in BMR. So this is NOx mainly come from on-road mobile, it means traffic. So CO come from on-road traffic, from the industry, and then from biomass urban burning. Non-methane VOC actually come a lot from biogenic, it comes from natural source. When I look at PM2.5 here, the PM2.5 come from on-road mobile source, okay, from industry, and from biomass urban burning. So this is to show you that's the source of primary particulate matter. It be road traffic, industry, and rise from urban burning. But then on-road traffic is the key source of many other pollutants, and these are precursors of secondary particulate matter, NOx and VOC, for example. Now for the emission, we need to put it in the grid. So this is 2.2 kilometers of grid to run the WAP CAMEX. And this is for VOC species, for PM2.5, and this is for NOx. And you can see the road network. It resembles road network. And VOC, it comes from many sources, not only from road, but also from biogenic. So the distribution is quite spread all over the domain. The model which runs, and then the model performance evaluation also was done. We find it satisfactory, and then we actually use a model to simulate the annual PM2.5 in BMR in 2016. And then this is the station where we have the observed data in that year. And this is we extract from the model and compare for 3 stations. ST61 is a PCD station, ST59 is PCD station, and then here the observed is a little bit higher or lower than the model, and especially we expect that observed would be lower than the model because the model is actually averaged over the grid of 2 by 2 kilometers, it means 4 square kilometers. But in some locations we have the source, that local source affecting, that's why I make it observe a little bit higher. So this is the annual level in 2016, and this is the red color here is showing the level that above the Thailand standard, annual standard of 25. When the color, the orange color here is from 15 to 25. The yellow color is actually from 10 to 15. So you can see that all over the domain we simulated, the level only higher than WHO guideline of 10 microgram per cubic meter. It means yellow, except for the very small edge here in the ocean and the effect by boundary condition. The health assessment approach, so we use a benchmark CE version 1.5, and this is I will not bother you with the equation here. What is new in our study, we actually try to calculate the global exposure modality model, it's called GEMM. And that model was newly published, and it incorporates data from 41 cohort study in 16 countries. And we use that data to calculate the relative risk value for BMR in order to calculate the modality of different types. And we quantify the avoided modality case if PM2.5 would reach benchmarks in every grid in BMR domain. So these results show a number of avoided modality cases associated with lowering PM2.5 in BMR to the benchmark. So the base case is 2016, right? And above here is the total, the avoided case in the in the BMR, and then the blue color here is for Bangkok, and this is dotted color is for other provinces in BMR. So you can see that if we reach definition guideline, the total number of deaths avoided in BMR domain would be 1,415. And in Bangkok, it's around 900 something. And then in other provinces in BMR, the level. This is a logarithmic scale. And similarly, if you look at 5, you look at 4, if you can look at the counterfactual concentration, it means the lowest concentration we could measure, then we can actually avoid number of deaths around 3,000 deaths per year in Bangkok due to the exposure to PM2.5. So the health effect in terms of the spatial distribution on GridNet, and this is number of avoided death case, both non-communication disease, okay, and lower respiratory infection. So if PM met WHO guideline of 10 micrograms per cubic meter, so you can see the level here. This is inside the city center where the level of PM2.5 is high. And if we cut down to 10 micrograms per cubic meter, so we could avoid the number of deaths from 5 to 10 deaths per grid. So summary and outlook. So the summary, the monitoring show very high level of PM2.5. Observe, especially in dry season. The level in dry season is about 2 times above the wet season. And the peak of PM2.5 in BMI is in this December, January, and February. So it means in dry period when we actually sometimes have the effect of the high pressure ridge. So that means the stagnant air. For receptor modeling, it major contributing source factor to PM2.5, being traffic, biomass urban burning, and secondary inorganic air zone. And secondary inorganic air zone, where we look for the source, we need to find precursor from the both local and regional transport pollution. For the emission inventory, it shows that major source of the primary PM2.5, especially black carbon, was traffic, and it mainly diesel power traffic. Then we also find a large part actually from crop residue urban burning and from industry. What convex dispersion model shows that PM2.5 is high in populated city center. That's why if we can reduce the level of PM2.5, at least to meet the current WHO guidelines of 10 micrograms per cubic meter per year, annual, so that we can avoid number of deaths, huge number of deaths actually in the city center itself. The future efforts, we should improve emission inventory and modeling efforts and use for effective air quality management, and also try to do online focus of PM2.5 and ozone air quality, because we talk a lot about PM2.5, but ozone actually also an emerging issue, and both PM2.5 and ozone are interrelated, and ozone also a climate causing pollutant. We did a clean air action plan developed and implemented effectively for BMR, or at least for Bangkok, to show countermeasures to try to stop urban burning, improve the combustion, and remove the dirty burning in industry. So one of the key concern during the episode, the people ask where that pollution come from. It come from the local source, or come from the nearby source or nearby country. So these questions should be answered, and using an integrated emission inventory and modeling approach, and especially not talk about the annual average, but should focus on during episode to show. During episode, say that pollution comes from neighboring country, so we would not do anything because most of them come from neighboring country. But if we can show the very clear picture that during episode, most of pollution comes from local sources, so then the efforts would be actually prioritized for the local sources. Thank you very much, and I would like to acknowledge that the project for JICA Research Institute and ESCAP for their contribution in this project, and then the AAT PhD project for emission inventory, and then AAT student research staff. We published these 2 papers already, but we have around 2 more papers at least in the pipeline. So thank you very much for your attention.
Thank you, Khun Kim, for the interesting presentation. And we have a question from my end. And you have rightly identified that there are varying levels of toxicity for PM2.5 particles.
We cannot hear you.
Sorry, can you hear me now?
Yes.
Okay, perfect. You rightly identified that there are varying levels of toxicity for PM2.5 particles, depending on the sources like traffic or biomass burning. My question for you is, depending on the varying levels of toxicity, would you expect significant differences in projected mortality? Can everyone else hear? I'm sorry, I'm just trying to. Can you hear?
Sherry, yes. I cannot hear your question.
Yes, Khun Jae, we're hearing you clearly in the meeting. Khun Kim, could we ask you to perhaps stop sharing your video?
Khun Kim, maybe you just have to, there's a cross at the top right corner. You will just have to click on that. Is it okay if we move on to the next presenter and I can go back with the question after the end of all the presentations? Abigail?
I can hear you now.
Oh, okay, okay.
I can hear now, if you can repeat it.
Okay, okay.
But then it stopped.
I'm sorry.
Okay.
Yeah, so
it's the internet is not stable. You can come back or you can type the question on the chat box. I will answer it. Thank you.
Sure. I can do that. And in the interest of time, I'd like to invite the next presenter in the meantime. That's Khun Chayut for presentation.
Hello, can you see my screen?
Yes, we can.
Okay.
Would it be possible to put that in presenter mode? Thank you.
Okay. Actually, today is the presenter is Dr. Thitiphorn Sukyael, but she has some duty. So I am Chayut Pinitkha. I'm going to present instead of her in this topic, the burden of disease attributable to ambient air pollution in Thailand. We both came from International Health Policy Program, Thailand, which is under the Ministry of Public Health. So this is the outline of my presentation today. Introduction of organization, general methodology to estimate in our project, and update you the completed project and ongoing project, and let's talk about the conclusion. So we both in burden of disease Thailand, which is under International Health Policy Program from Ministry of Public Health. So the main responsibility of burden of disease Thailand is to develop the burden of disease indicator to qualify them and inform the public health policy makers to support the policy formulation to improve health system at national level. And it is our example of prioritized risk factor in Thailand in 2014, which is the latest. We update 3 years per time. So we currently do the 2017 or 2018. So this is the prioritized risk factor in Thai population. which is including the ambient particulate matter. So the general methodology framework that we use to estimate the burden of disease or health impact risk is come from this framework. So we use the air pollution data in national level, model level or monitoring level, and population risk. And we literature review on the concentration response function. And we have a background data on mortality and morbidity from Ministry of Public Health. And we then estimate the impact. So we have three main components: exposure data, population data, and concentration response function. So this is the methodology that we use to estimate the burden of disease to air pollution. We call them the comparative risk assessment. So this is framework and methodology that we use to estimate. First is come from the station. Concentration map is to build the concentration map and use the population and relative risk and the counterfactual concentration and mortality, premature death. And it is our example of we estimate the burden of disease attributed to air pollution. It is our previous published paper on the air pollution Thailand. We use whole country of monitoring station to map the concentration in area and use the population distribute data with this following equation on the relative risk. The assumption is on relative risk is based on this equation, and we calculate the PAF or population attribute fraction. And we use PAF to multiply with the baseline of mortality data. And we found that the results of this study is we found that about 6% from total mortality attribute to PM2.5 is 6% in total burden in Thailand. And ozone, we found that 0.3% of total burden, which is related to the global burden of disease study, with this collaboration of the WHO in 2015, with estimated almost 8% and 0.1% of long-term exposure to PM2.5 and ozone globally. And it is another project in the burden of disease, which is mainly focused on the local region in the northern area of Thailand. The Northeast project, the annual one came from January to April, and it is the factor related that we reviewed for the health information. For example, the burning of land from farming in northern, also the ambient from transboundary condition like Burma and Laos, the climatic condition and topography of northern Thailand. So this is the distribution of daily distribution of the PM10 concentration in the province in northern area, and found that compared to the reference period, we found that it's extremely high in the northeast period in northern Thailand. And the study used the time series regression to investigate the short-term association between exposure and health outcomes. This study, we select the outcome from all-cause mortality, cardiovascular disease mortality, respiratory mortality, and we include the outpatient data visit, which is cardiovascular disease and respiratory disease, and use environmental tracking from the pollution control department from PM 2.5 and PM 10. And we found the association. First of all, we found the ratio of the PM concentration is almost 4 times higher than the baseline condition. January, April to May to December is the highest is in Mae Hong Son in the left one. Sorry to display in Thai. The Mae Hong Son is on the left one of northern Thailand, almost 4 times or more than 4 times higher risk, the ratio of PM10 concentration. And we found the risk of death from all-cause mortality in Mae Hong Son is almost 2 times higher risk compared to the baseline condition in this period of the northeast condition in northern Thailand. And it is from Chiang Mai, from Lampang, Nan, and Lamphun. It is for all-cause mortality. And the next one is risk of death and hospital visit with the cardiovascular disease during the northeast period. 3 times higher in children groups age about not more than 14 years. 3 times higher risk with the CVD in northeast period. In Nan as well, we found the elderly people has 2 times higher. In Nan is the on right one on in the northern region, 2 times higher. And it is the risk of death of hospital visit with respiratory disease during the northeast period. More than 4 times higher had the risk of death from respiratory in Mae Hong Son in northeastern period. And Lamphun in elderly people is 4 times higher. So is there a risk? Of course. And it is we try to better understand the emission, the source, the exposure misclassification on the distribution of population, the time activity, the mixture of air pollution and ICD-10 code from the death registration of the Ministry of Public Health, socio-economic status, occupation, age, or activity of the population. So our ongoing project is from the burden of disease is to use the health need assessment tool. The health need assessment tool is the subnational visualized subnational health data. We have 2 figures. First one is we would like to map the outpatient data and inpatient data to explain to explore the healthcare utilization and mortality map by district to find the association between the air pollution related cause of disease and risk of death with the mortality map by the province. And further, we would like to add in a socio-economic status and other covariates in the model to better find the association between exposure and health outcomes to improve the accuracy or improve the reliable data of burden of disease. This is where we want to try to do more advanced in the next step. So our modeling, the previous one is based on only the monitoring station, ground-based monitoring station. We would like to explore more on the more advanced methodology to quantify and prioritize the contribution of the PM 2.5 in burden of disease estimation to prioritize the risk factor and disease by hotspot analysis or spatial clustering and machine learning approach to link between the morbidity and mortality outcome in Thailand. So let's talk about our conclusion. Is in our project is aimed to quantify the magnitude and distribution of the disease burden caused by the ambient air pollution in national level, and we would like to explore an integrated methodology on the exposure assessment, maybe using interpolation model from empirical data, chemical trace transport model, population distributed exposure, and health impact function that have recently updated in this year. And ongoing project will be developed to increase better understanding and will inform to local policy and planning and research communication. So our next project should be integrating more advanced method and think about the transboundary condition on the pollutants that come to Thailand and mixture of pollutants and source combination. So thank you. This is end of my presentation, and if you have any further information or contact, you can contact Dr. Thitiphorn Sukkel in this email and or me, Chayut Pinika, and at this email. So, and this is a channel to contact in International Health Policy Program Thailand. So thank you so much for attention and on my presentation.
Thank you, Kunchai, for the presentation. And I have a question. You mentioned that there are a lot of complexities with modeling air pollution impacts and mortality in general. So what kind of support would International Health Policy Program like to receive to address the issue of transboundary PM 2.5 sources?
Yes, the transboundary condition is maybe out of interest in the national level of the burden of disease in Thailand, but we really interesting in the transboundary condition, and at this time we try to have the network capacity building on the China University on the southern China to have more analysis in terms of utilizing the remote sensing data on China, and could be the transboundary transport the air pollutant in northern of Thailand. So yeah, this is my answer.
Yeah, thank you. Definitely collaboration and knowledge transfer is one of the most enabling things we can do to address transboundary sources, especially given the fact that it's across, it affects a lot of countries, and it's always across boundaries, which is a multi-country or a regional issue. Thank you for the presentation. I would like to invite Khun Thang Chai for the next presentation.
Thank you very much. So let me make a screen sharing. Okay, I think I have to share the entire screen. So can you see my screen now?
Yes.
Okay, thank you very much. So good morning, everyone, and particularly, I would say a very good morning to my professor, my advisor, Professor Kim On from AIT. So I'm very glad to meet you virtually in this meeting. And so my name is Thongchai Khnapkyaw. So I'm now at the Faculty of Public Health, Thammasat University, and the topics that I'm going to present is about the detection of PM2.5 plume movement using the IoT ground monitoring data. So in my presentation, so I will focus on the study area, methodology, flow, that and the tools that we use for the data analysis, combining with the data transformation, data visualization, and data analysis, and the last one will be the summary. So in my presentation, you will see something that differs from other people's, because at the morning section, this morning section, we are talking about the chemical analysis or the monitoring of the data using the standard equipment. But in my presentation, we try to introduce the low-cost IoT sensor, which we can have a network or a large numbers of the sensor through all the countries, and with the density of data, so we can have the ability to understand the situation and to forecast the future phenomena related to the air pollution. So before I'm going to give the details of my presentation, I will introduce the teams that working on this project. So we have Dr. Adison, which is the principal investigator from Asian Institute of Technologies. We have Dr. Suni, who is the data science and statistical analysis from Thai Australian Technological Service Center. She is formerly the lecturer from Sri Nakarin Virod University, and myself, which is I'm on the environmental science perspective. So you see that what I try to give this slide presentation, because I'm very happy working with the teams, because we have a good combination. So we have computer science or computer engineering as the structures of the work, and we have data science as the tools that are the techniques that we can use for the analysis. And myself, like a domain of the knowledge in environmental science or engineering. So in the topics that I'm presented in the phase one, the result from the phase one project, which is about the redeployments of the sensor node, and we try to detect the movements of the PM2.5 plumes. And now so we are at the end of, I say that phase 2.1, that we are expanding the sensor network to detect the forest fire. We try to find the patterns or the models using the machine learning, and to identify which one is the influence or impacts from forest fire in the areas. And in this phase 2.1, we also have a lot of queries or questions from people that when we use the sensor, what is the validity and reliability of the sensor? So we make a detailed analysis, QA/QC of the sensor before we deployment. And we announced is like working on the paperwork on phase 2.1 to disseminate our results for public. And at this time, in the next 2 years, we have another phase that I can say that phase 2.2, which is the OLAP phase, with phase 2.1. So we are now trying to implement the solar cells and the LoRa technologies in our sensor to install or to deploy in the remote areas. And the purpose of the project is for the forest fire surveillance in the northern parts of Thailand. And this is our study area. So in the phase one, we are focused on the detection of the PM2.5 plume movement, and we integrated the area in Tak Province, which is have very high concentration of PM2.5 or PM10s, at the same as other northern regions of Thailand. So we deployed several sensors, maybe around 10 to 20 sensors in this area, and we try to group it by the zone. So we call MS refer to Mesot, MG refer to Magazine, and TS we Thai Samakhi. This is along the wind direction, the monsoon directions of Thailand, which is northeast and southwest direction. And at the nearby areas, we have also one station from the Pollution Control Department, which is 7060. So we can compare our sensor data with the data from Pollution Control Department, which is the reference or the standard data that we can have in that area. And this is the results from comparing between our sensor data and Pollution Control Department data. So the red line is our sensor for PM2.5 readings, and the blue line refer to the data from the standard reference, which is from Pollution Control Department. So we can see that in the same times during the open burnings, our sensor we give the values higher than Pollution Control Department, but the key interest from the sensor is that we have the relatively fluctuation, which is the same with the data we got from the reference data. So with this relatively reading, for example, when the value is getting high, so our data is also getting high, and when the reference data is getting lower, so our value is getting lower as well. So with this sensitivity of the sensor, we can make use of the analysis for the to see what happened in the area. And the right figure showing the correlation between our sensor and PCD data. So you see that the R square is around 0.9, which is quite high. So if we would like to adjust our sensor value, we can use also this relation. And for the methodologies that we work in the area, so we have the data collection and from our sensor. So the data will be normally collected every 2 minutes, and then we make a transformation of the data using one software we call Petrol Data Integration or PDI. So this software will help us to transform the data from 2 minutes data to be 15 minutes or 1 hour of data. Imagine that you have a huge number of the data. You have every 2 minutes, you have every hour, 24 hours, and the data will be a year and for around 20 sensor nodes. So we would need some software to assist us in making the data in the format or in the structure that would be easy for us for the analysis. And then we visualize the data using the Power BI, because during the study period, we will see something happen in the area. We will see there's some typical case, for example, very high particulate matter in some particular days or some particular hours. So in this case, very easy if we can use the software, a kind of dashboard principle. So we use Power BI to visualize our data. So by using this one, we can drill down to our data to explore the data before we go into the analysis. And the last one, we use the R program or the statistical package, which is the open source package for the data analysis. And now we try, our people from computer science try to make it in the pipeline data analysis. Once we know the thing inside, and then we're going to put it to the computation nodes for the automatic calculation. And this is the website for the data visualization. If you would like to see our data, you can go to this website, hesmon.in.th. And this is examples of the data transformation. I will not give the details how we are going to do this, but this is just an example of the tools that we use for the analysis. Even from the environmental background, but the tool will not be difficult, so it would be very straightforward and quite simple. Once we understand the flows of the data, and then we can use the tool. And the second tool will be the data visualization. So as I mentioned, for the data visualization, you can make the time series plot, you can make the spatial distribution plot, and then if you would like to see particular days or particular hour, you can just click on the panels on the level that you have. So the graphical pictures be changed accordingly to the data that you are selected. So this is a kind of dashboard technologies. And then we use the R program for the data analysis. And this one is an example of the, for example, like regression analysis. We would like to see like if we are going to predict PM2.5, which one is the contributors or which parameters that affects on that one, and then we can see also the significant levels of the data. This is just an example, and from the results of our study in phase 1, I would say that so we try to understand the effects of the hotspot and wind to the PM2.5 in the area, and we use Magasa and as the predictor, or we can say that we use Magasa at the dependent area. So we would like to see how the other zone that affect to this zone, for example, and then we select the data which is the wind day and no wind day. So the data in the wind day to see that what going to be the main contributor to PM2.5 at Magasa area. If in that day we have the wind day, so from this data you will see that we have the concentration of PM2.5 from another zone, which is TS lag 2, that have a higher contribution to Magasa in that wind days and in the no wind days. So if the wind is like if the wind is calm or near to zero, what's going to happen? So we will see that the contribution from their own concentration in lag 1 is higher, increasing. I would say that it is increasing comparing to the contribution from another zone. So the lag 1 going to represent the PM2.5 concentration at 15 minutes before, and lag 2 is the PM2.5 concentration at 30 minutes before. So by using this analysis, we understand how the particulate matter concentration is changing in the areas. And for the effects of hotspot, we pick 2 days with the high hotspot and no hotspot. So in the high hotspot, we will see that their own concentration from their own zone has a very high contribution to PM2.5 concentration at Magasa. But if we have no hotspot, so you will see that the contribution from their own lags or from their own zone is reduced significantly from 0.97 to 0.3, and we have another contribution from the lag 2 of the another zone or from the upwind zone, and the R square, I mean the coefficients of the determination is vary depending on the situation. And by this analysis, we understand how the effects of the winds and the biomass burning hotspot contributed to the particulate matters in the downwind zone. And then from that knowledge that we have from the previous slide, we try to make a forecasting of the next 15 minutes PM2.5 in the area. So as I mentioned that we know that the main contributor to particulate matter in the area is the first one going to be biomass burning or hotspot, and this one could be represented by the lag time concentration of PM2.5, and another parameters that contributed to PM2.5 in the area, which is wind speed and wind direction. So by this forecasting, we categorize the data of wind into 4 categories, which is calm wind, light wind, and moderate wind. And then we sort the wind by only the predominant direction. So at that moment, at that particular month, around at the mid of March to mid of April in 2018, so the predominant winds is from southwest direction. So we sort only the southwest direction to forecast the plume movements of the PM2.5. And from this one, I would say that if you see the calm wind, if we have the calm wind, the concentration from their own zone or from has higher contribution. But once it comes to light and moderate wind, so we can see the contribution from another zone. And by this one, so we can see that the wind speed and wind direction can transport and can move the particulate matter from the upwind zone to the downwind zone. And if we have a look on the levels of prediction in terms of R square, so we can see that it is around 0.9 for the R square. And for the more information, so you can go to our publication. So not only the forecasting data that we have done in that work, but we also do analysis of many correlation between PM 2.5 and other parameters. So I'll come to the conclusion or summary quickly of the research findings. So if we have the real-time data collection, so in terms of low-cost IoT sensor, so this IoT sensor, so we help us understand the PM 2.5 plume movements and formation in the area. And the second one, by the low cost of the IoT sensor, I mean, comparing to the commercials or to the standard equipment, so we can afford the large scale installation of the data. So we have more data. So in terms of the data size, so the more of the data we have, so the higher ability that we can use the data to understand the situation and to predict for the futures. And you see that if we mention about the lag time concentration of its own node or its own zone, so it has very high contribution to the next 15 minutes of that zone. So by using this data, and if for the every 15 minutes, so we have the higher ability to know in advance, like the next 15 minutes, the next 30 minutes, or even the next hours, what's going to be happen in the area, and the levels of the prediction in terms of R square is quite high, around 0.9. So it means that we can explain the results or the equation by using that data around 90%. So, and the last one from that I could summary from what we have got from the analysis, by using this one and by the abilities of the prediction, so we can say that with the timely prediction, so we can implement or we can do something to manage, to tackle the PM 2.5 crisis in the area. And I think this is the end of my presentation. Thank you.
Thank you, Dr. Thongchai. And I think you have a question in the chat, and I can type my question in the chat. In the interest of time, we can move on to the last presentation, which was the first one, actually. I would like to invite Dr. Pham to present for the last 15 minutes.
Okay, thank you. Thank you very much. I will answer in the chat.
Are we still having a technical issue with Dr. Pham?
Yes, I believe we'll need to accommodate that presentation in a later session.
Okay. Okay, sure. So I think we can conclude the session now. And I'd like to invite Matthew to recap and close.
Thanks everyone for your participation here today. We hope that we've properly captured all of the emerging scientific consensus and recommendations for future study. As we mentioned in the opening, we will be circulating the overall findings of this meeting for review and adoption within the next week. So in order to avoid keeping everyone on an eternal WebEx today, we will conclude and adjourn this session here and look forward to seeing you all again tomorrow, where we will continue the thread of findings that were discussed today. Thanks very much and look forward to seeing you tomorrow. Over.
Thank you. Bye-bye.
Thank you.